Today we are going to talk about fine-tuning large language models. Fine-tuning large language models. There are a lot of language models out there. Many of them, they have released weights in many instances. But when you have your own data set, you may want to fine-tune the language model on your potentially private data set to have a better model for the application that you have in mind. But that immediately poses some challenges because of the size of these models. For example, GPT-3, as we talked about, it has more than 175 billion parameters. Some models, like Palm, they have even more parameters. And these days, people, they use a mixture of experts. They use like even bigger models. So the size of the models, they are huge, in the order of hundreds of billions of parameters. So that means even storing the weights of your model, it is quite challenging on, let's say, one single GPU, because you're storing hundreds of billions of numbers. And you want to do some compute on top of it to potentially change weights of your model for your specific application. So there are issues in terms of the storage. There are issues in terms of the compute. And you need to have a lot of memory, a lot of compute in order to fine-tune your model. So with this problem, to deal with this problem, there are several solutions in order to make both storage and compute lightweight for many downstream applications. Okay, so we are going to talk about not all of the solutions provided in the literature, but probably most successful solutions that have been adopted widely in practice. Okay. So one set of solutions is called adapters. So the idea is quite simple. So the idea is, okay, so you have a big model. Let's say I have a large model. Instead of changing all weights in my model during the fine training process, I'm going to specifically have some particular layers called adapters that can potentially be changed during fine tuning. So I'm not going to change the entire weights. So these are going to be the same as the pre-trained model, same as before. But some layers are going to be, some parts of my network is allowed to adapt to the particular setup that you're fine-tuning. So that's basically the idea of adapters. Obviously, it is good because you can reduce the number of parameters that are updated during the fine-tuning quite a bit, depending on how many layers do you have in your adaptation. So a particular family of adapters is called LORA, short for low-rank adaptation. There are different implementations of adapters. Obviously, I won't be able to cover all of them, but I'm covering like the most successful instance of this family. As I mentioned, it is called LORA, short for low-rank adaptation. Okay, just to give you a context, there was a paper by Akajanian that basically, an ETL that basically showed if you look at model parameters, if you look at the distribution of model parameters, they are intrinsically low rank. They have done some empirical analysis showing the distribution of model parameters have low rank intrinsic dimensionality. Okay, and in many cases, it has been verified. In fact, we recently had a paper in NeurIPS called diffuse redundancy, where we showed that you can randomly sample. That was for a classic ResNet model. You can randomly sample the features in your penultimate layer, and the model performance is pretty solid. So you don't really need all of the features in your last layer. You can randomly sample, and the model performance is still good. That kind of shows there are a lot of redundancy in the weights of your model, that even if you drop quite a few of them, the performance of the model, at least on the benchmarks tested, remains pretty much the same. So another paper followed up on this idea, paper by Edward. And they argued that not only the model parameters, they have quote unquote low intrinsic dimensionality, but also the changes in the model when you are fine-tuning, it has quote unquote low intrinsic dimensionality. That was basically one observation that they made empirically. Changes in model parameters during fine-tuning often has low intrinsic dimensionality. That was basically the observation that they made. Based on this observation, they suggested this really simple idea. So suppose you have a set of weights in your model, W, and you want to update these weights. Let's say in fine-tuning, say starting with W0, these weights go to W0 plus delta W. These are the changes that you are making to your weights during the fine-tuning. Okay. So instead of writing the changes as W0 plus delta W, the assumption is you're going to write this as W0 plus 2 matrix B multiplied to each other, B times A. And we are going to ensure these matrices are low rank, meaning that if, let's say, your delta W, the dimensionality of this matrix is D by K, just as a general notation that you might have, D and K, they can be big numbers. You're going to assume the dimensionality of B is D by a number like R, and the dimensionality of A is R by K. Obviously, the product will give you a matrix D by K. But if R is much smaller than the minimum of D and K, the product matrix B and B times A is low rank. And that is constrained. The rank is constrained by the number R. Then rank will be up to R. Okay. So if you think about going from this direction to the other direction, the process is actually quite expensive. Right? So because if you think that first you are going to compute delta W and then compute a low rank decomposition, usually that requires an eigen decomposition or a singular value decomposition that is not cheap. In many cases, it is cubic or close to between quadratic and cubic, depending on the matrix that you have. This is quite expensive. But it is not the direction that we need. The direction is to go from this matrix B times A to delta W, which is simply a matrix multiplication. And that is quite easy because the rank R is significantly lower. So that means instead of saying that I'm going to have a general perturbation in my weights, delta W, and then maybe like projected to like, some sort of dimensionality reduction, we are going to assume the change is explicitly in the form of two matrix multiplication, B times A. And these matrices are constructed in a way that the combined matrix B times A is low rank, because R is our design choice. I can pick whatever R I want, and that can adjust my complexity. Just to give you an example, okay, so let's imagine you have a delta W. Let's say it's in a matrix form, 200 by 200. You can imagine 200 different vectors of size 200, just to illustrate. Therefore, the number of parameters that you have here is how much? The number of parameters is 40,000. But instead of updating these parameters individually, so LORA, what it does is constructs two matrices, B and A. Let's say B is 2 by 200 and A is 2 by 200. So the overall matrix product is going to be again 200 by 200. But the number of parameters that you have is just 800, 62 times 400 in this case. Significantly lower than the original 40,000 parameters that you needed to update. Simple idea, but really, really effective. Okay, so you can apply LORA on different layers, on different matrices of weights, especially if you have some empirical evidence that the changes in those weights during fine-tuning is likely to be low rank. That is better to apply LORA, because in that case the loss in terms of the full fine-tuning will be minimal. So in transformers, by the way, in terms of the initialization, Usually, one of these matrices are initialized to be just 0 as the initialization, and the other matrix, the values of the other matrix is randomly sampled by a Gaussian. That's the initialization that people usually use. And the choice of the 0 for one of the matrices is to ensure when you don't do anything, the change is 0. So you have your original pre-trained model. So in transformers, usually this is used in the attention layer, but you can use it in other layers as well. In transformers, used in attention layers. In attention layers, you have different matrices, right? For the query, for the key, for the values, and there's like another projection matrix. You can use LORA on each of them individually, on one of them, combination of different LORAs you can have on different matrices, and people, they have done a lot of empirical studies. Okay, so in practice, one note that I want to make, this matrix product, this change that you have, is often scaled by a number, alpha times r. This r obviously is the rank, or the upper bound on the rank that you have, and alpha is a constant. It's a scaling factor between 0 and 1. So if alpha is 0, it means the effect of b times a, effect of fine-tuning, is like nothing, right? Because you multiply it with 0. You recover always your original model. If alpha is 1, you are basically allowing the weights in that particular layer that you are applying LORA to change quite a bit. That's maybe we can call it fully fine-tuned, even though like fully, it doesn't really mean fully because you still have the rank constraint, but you get the idea. And somewhere in the middle, it provides you some sort of adjustment, how much distance you want to go away from the original model and how much effect of fine-tuning that you can have. And it really depends, the adjustment depends on the size of the data set that you're fine-tuning. If you have a relatively small data set, you don't want to overfit on that particular data set. You may have like some bad behaviors because you're overfitting to a small data set. If you have a relatively decent size of data set that you're fine-tuning, maybe 100K samples, you can get close to alpha 1 for your fine-tuning. But that's something that has to be empirically studied. Okay, so that is it. That is LORA. So if you're seeing people, they say, oh, I'm fine-tuning using LORA, that is it. Instead of the full change, you use b times a. And b is a matrix of, let's say, a particular size times r, and a is a matrix of r times a particular size. And r is your design choice. You can use 2, you can use 4, you can use 8, whatever empirically you can get some good results. LORA was first introduced for language models, but you don't have to only use it for language models. In fact, there are LORAs used for diffusion models, text-to-image diffusion models. Let's say if you have a particular style of images, you want to generate objects with particular texture or whatsoever, you can have those samples, fine-tune your model, and you will get some interesting generation. In fact, you can look it up, that there are some really interesting adaptation of diffusion models using LORAs based on particular data. All right, so that's basically one technique for fine-tuning. So the idea here is to reduce the complexity by low-rank adaptation to allow big models to be fine-tuned even on single GPUs. That's basically the main idea. Okay. So let me pause and see if there are any questions before I move to another set of techniques in order to make the fine-tuning and the storage of these models more efficient. Yes?
The first paper you mentioned talked about how the parameter itself also has low dimensionality.
Yeah.
Doesn't also imply that you can just use smaller parameters?
I'm sure it does. So basically the question is, if you are saying that the parameters are also low dimensional in terms of their intrinsic rank, and the LORA is basically saying that changes are also low dimensional, can we combine the two ideas? And I'm sure people, they have done it. Yes? So you basically assume the changes is in the form of B times A. So you are backpropping to update each of these matrices that you have in your law. Right, any other questions? Okay, so if not, let's talk about another angle to this problem. Again, I started the lecture by saying that, okay, we have like these huge models. Okay, so problem. Large models, like sometimes, large models is, a feature saying that, oh, I have a large model, large language model, large text-to-image model. But in some instances, you may have like a low memory to store your model. So this will be a bug for you. Let's think a little bit about it. So when you are storing your model, you're storing weights of your model. So you have, let's say, weights for your MLP layers in transformers. You have, weights for your attention layers. So how we store these weights? That's basically the subject of the next part, and how we can efficiently store these weights. So in many cases, these weights are real numbers. So we need to basically store some real numbers, and perhaps like the most common format for storing real numbers is float 32. That's the format that we use to store real numbers in many instances. Okay, so I'm going to talk a little bit about these different formats, because that's going to play a big role, because at the end of the day, we want to store these models and we want to update these models potentially on one GPU. So 32 means we are going to store every number with 32 bits. So that's where the 32 comes from. So I have a budget of 32 bits. So I need to spend this budget perhaps carefully. Okay. All right, so how are we going to spend the budget? So obviously, one bit is going to be dedicated to indicate the sign. Either that number is positive or that number is negative. So that's called sign bit. There's no getting away from that. So one bit for sign, plus or minus. We are going to have 8 bits for a part called exponent. And how many bits are left? So we started with 32 bits. We spent 8 bits on a part called exponent, 1 bit on sign. So we are left with 23 bits. And this part is used for characterizing the fraction part of the number. We're called Menesia. All right. Just to give you a rough idea how it works, because okay, so I have all of these bits. You know, what is my number at the end of the day? Let's look at one example. Okay, so let's assume you have a positive sign. That's for the sign part. For the exponent part, you have all zeros, and then you have 1, 0. This is the exponent part. And for the fraction part, you have all zeros, and at the end you have 1, 0, 1, 0. This is the fraction part. So one convention, now that you have strings of bits, you want to basically see what real number it represents. So one convention is as follows. So you look at the exponent part, you look at the 2 to the power of this number in the binary base. So here, basically the number is, everything is 0, 1, 0 in the base of 2, which is basically 2. So this part represents a number like 4. And in some cases, you know, I won't go into the details. You may subtract off some base number from the exponent, but that's less important. Okay. So for this part, this represents the fraction. You're going to basically start from the right bit, and for each of them, look at whenever you have a 1, you add like 2 to the minus of the relative position of that number. So you start with like 2 to the power minus 0 times 0. For 1 is like 2 to the power minus 1. So this one is 0. And for this one is 2 to the power minus 2. Minus 3. Right? So you get the number here. I don't know what is the number. And let's call it, I don't know, 0.4, just, you know, as a guess. So you are going to add 1 to this number. So this is going to be 1 plus whatever number that you get here. I'm assuming it's 0.4. You're going to multiply with this 4. You are going to multiply with the sign that you have. Let's say 1.4 times 4. And that's basically the number that you get. That's the real number that you're representing with these bits. So the reason I did this is just to give you a little bit of a feeling that what is really happening here. When we are talking about float 32, are we like, what are the 32 bits? Some parts of it are used for the exponent, some parts of it are used to represent the fractional part, and 1 bit is used for the sign. Okay, now that we have this feeling about how we are storing 32 bits to represent real numbers, now I have, let's say, 100 billion plus 100 billion numbers. Even to store these many numbers, it's a little bit scary, right? So any saving that you can make can be a huge saving in terms of your storage. So obviously one saving is that, okay, do we really need 32 bits? Can we reduce the number of bits that we have for the exponent, the number of bits that we have to represent the fractional part? Obviously sign has to stay there. And there have been a lot of papers to basically show by reducing the precision how much performance loss that you suffer. So in fact, in many cases, you really don't need 32 bits. If you go even down to 16 bits, the performance is more or less the same. And the way that people spend their 16 bits, for the sign, obviously, you need to have 1 bit. For the exponent part, you spend 5 bits. And for the fractional part, you spend 10 bits. That's the 16 bits. So you really don't need, especially in large models, to have 32 bits representing each base. You can maybe reduce your precision a little bit. Right? So you don't have all of the floating numbers, but still you get pretty decent performance. But now you may say, okay, let's just push it further and further. So what about like 4 bits? Let's say if I give you 4 bits, how would you spend that? 1 bit has to be spent on the sign, right? So there's no way getting around that. So that's 1 bit of sign. Then you're left with 3 bits. Okay, then you have basically 2 choices, right? So you want to have some set of bits for the exponent, some set of bits for the fraction. Usually people spend 2 bits on the exponents and 1 bit on the fractional part. But you can do the other way around. In fact, some papers, they don't even consider any bits for the fraction part, and consider 3 bits only for the exponent part. Basically, you can try with different thresholds with different representations. But broadly speaking, when you go below 16, your performance suffers quite a lot. Like from 32 to 16, it is okay. But when you go from 16 to 8 or even worse to 4, you see drop in performance. Significant drop in performance. Because obviously, like now you are reducing the precision of your numbers, right? So your weights might change quite a bit when you are doing such compression. Okay. Then the question is, okay, so why do we really need to have fewer bits? The main reason, in many cases, is the storage. Because we need to store all of these numbers, perhaps like 100, tens of billions, some cases hundreds of billions of numbers, ideally on one machine, on one GPU. Because then you have to deal with the synchronization. Maybe some parts of your weights are like on one GPU, like some other parts of your weights are on other GPUs. I'm sure people, they have done like amazing things in terms of like synchronization, but it is not clean, right? It is not easy, right? So the easiest is like you have one machine, you have your model, you fine tune on that machine, you are done with it. So that's basically the reason that we want to reduce the number of bits. So, but maybe reducing the precision the way that we are doing is not the right way. And because of that, people, they have started to think about quantization instead of just reducing the precision the way that we are doing. So quantization, so the idea is basically compression, right? So you are storing your weights in a compressed fashion, hopefully by having as little as little as much of information loss. So one of the successful ways of model compression is called 4-bit normal float. Again, we are going to use 4 bits, right? But instead of the standard way of reducing the precision of your numbers, we are going to do something else. So in 4-bit normal float, the idea is to look at the distribution of your weights. Let's say you have a pre-trained model. And if you look at the distribution of your weights, in many cases, it looks like a normal distribution. This is an assumption. It might not be exactly like normal distribution, but if you empirically look at all of these big models, the distribution looks like a normal distribution. Looks like a normal distribution. What looks like a normal distribution? Distribution of weights. Okay, so this is an assumption I want to highlight. Okay. So they're picking quantization levels to ensure that, roughly speaking, at each quantization bin, you get the same number of bits. So if your density is higher in one area, then the quantization levels will be closer to each other, versus if you're on the tail part, your quantization level can be further away from each other. So in other words, if you look at the areas that you have here, more or less you want to have the same areas. Roughly speaking, same areas in each quantization level. Therefore, when you are using codes to represent each part in your space, let's say you're using 4 bits, obviously you're going to have 16 different regions in your space. More or less, the number of weights assigned to each bucket is the same. So if you start, let's say, with 16 billion parameters, do we have a model with 16 billion parameters? I think we should have a model with 16 billion. So then you, roughly speaking, get 1 billion each. 16 billion parameters. And in a sense, this is information theoretically optimal because you get a uniform number of weights, number of members in each bucket after the quantization. However, like this doesn't mean anything 1010, right? So we are not using any manipulation like before in order to turn this into a real number. This is a code. It's a quantization code. And you can have different strategies for your decoding. Saying that, okay, so what number this is assigned to? Maybe look at the values in that bin, look at the representation of that, maybe have some number randomly generated from that bin. You can look at like different decoding strategies. Okay, so this is the code. Okay, so that's basically the quantization. This helps a lot in terms of the storage, because now you can actually have 4 bits instead of 32 bits. That's an 8-factor reduction in the storage of your model. So 8-factor reduction. So that's basically the idea of the quantization. So we started with talking about LORA. The idea was to not fine-tune everything, only look at a subset of elements and only update them with a low-rank fashion. Next, we talked about quantization, which is a different angle, right? So basically, it's about storing numbers, how to effectively store numbers. So what would be a natural third step if you really want to get the benefit of the two? What would you call that? QLORA. There you go. Thank you. QLORA basically combines the ideas from quantization and LORA. Okay, so the way it works, if you have a pre-trained LLM, first you do the 4-bit normal float quantization that I mentioned. And so you get a quantized LLM. So for storing your model, you always store the quantized version. You don't store the actual bits. But the trick is that for compute, by compute I mean the gradient computation for the LORA weights, they use a 16-bit basically float version. On the fly, they use decoders, meaning that they map the codes to real numbers, and they use the real numbers, the 16-bit bits of real numbers in the compute. But the storage is done for 4 bits, and they don't decompress everything, because if they decompress everything, then you don't have any bits. And they have done other contributions in terms of really pushing the storage of the model to as low as possible. In fact, with QLORA, you can have a 33 billion parameter model fine-tune on a single 24 gig GPU, which is quite impressive, right? So it's a huge model. You can use a GPU that is not even like, super high memory, and you can do fine-tune on it. And there have been a lot of empirical works showing that the quality of the model is pretty good. So it is on par with a model of originally stored and computed using 16 bits. 16 bits of floats. Okay, so that is all that I have with respect to LORA, quantization, and QLORA. So let me pause and see if there are any questions. Yes.
Does the pre-trained LLM come as a GA format?
Usually 16 bits float. That's the format that it has here. But you can use it for even 32 bits models.
Do they come in as the low ranked version?
No. So the pre-trained model, it is not. The question is that if the pre-trained model comes in a low rank fashion, no. So basically the idea, your pre-trained model is basically set of layers in your transformers, right? So the attentions, the MLPs, etc., etc. So the lowering part is the adaptation part, that you wanna only change few parameters in your model, maybe few dimensionalities in your model, maybe on the weights applied for the queries or keys, and that's basically the LORA. So maybe time for one more question. Yes. So can you repeat the question? Quantization requires. No, the quantization is fixed. So we are not, that can be interesting to see during the fine tuning. Do you need to adjust your quantization? But in QLORA, the quantization approach is fixed. So we are not changing. All right. So we have about 15 minutes. So I'll cover one more idea about making fine tuning a little bit more efficient. So, and that is called prefix tuning. Okay, so in fine tuning, you are changing your model. And so in LORA, you're changing a little bit of your model. With adapters, you're changing maybe like, just the adapters. But you are changing your model parameters. In fine tuning, I would say some model weights change. In full fine tuning, all of your parameters can potentially change. In LORA, maybe just a subset of them, small subset of them. So the idea of prefix tuning is to keep the LLM same, keep the model unchanged. Don't change your model, but I want to have a more specific model to my data set. And let's say if I don't change my model, what else do I have? The input. Right? So the idea is to add some dummy vectors to the input in order to perhaps have that particular information about that the data set that you have, and you want your model to be tailored to that particular data set. So here's the idea. Optimize a small task specific, a small number of task specific vectors called prefix. So if you have a transformer here, okay, so you have input tokens as we have discussed before. But now you are going to maybe add some vectors as prefix tokens. And these are optimizable, these vectors. You'll fine-tune your model, but you won't fine-tune your model. Your model is going to remain the same. The only thing you are going to optimize over are these vectors for that particular task. Say you have a data set, questions, particular answers. If you do like regular, if you use the original model, maybe you're getting some performance. you're adding these vectors to provide additional flexibility to your model, and you optimize these vectors. In fact, in the paper, they don't even directly optimize these vectors. What they do is that they have an MLP that outputs these prefixes, and they have these vectors, input vectors to the MLP. So much smaller in terms of the dimensionality, and then you have the MLP weights. So these are the two weights that you optimize, and then you get your prefixes based on your optimization. Okay. So before like LORAs became super popular and easy to implement, this was a nice idea, and it can boost your performance without fine-tuning. These days, not a lot of people, they use this technique instead of fine-tuning. They use fine-tuning, especially with LORA. But I think the idea is very interesting and can potentially have other applications to add some quote-unquote task-specific context into the input, and have that information in the input rather than some other places in your model. So that was the reason I covered this as an additional technique that would be nice to have in mind. All right, so that is all I have in terms of efficient fine-tuning or adjusting your model to specific tasks. Let me pause here, see if there are any questions. Otherwise, I'll switch gears and cover another topic. Any questions? All right. If not, let's switch gears. Next, I'm going to talk about retrieval augmented generation. Retrieval augmented generation, or short for, in short, called RAGs. Okay. So when you have an LLM, let's say you have an LLM. You're train your LLM, let's say, on Wikipedia passages, on like different inputs, and then you're asking a question to this LLM. Hopefully, it can provide you some reasonable responses, and obviously, it depends on the training set of that LLM. There is no magic here. Right? So if your LLM, for example, had not seen any facts about, let's say, Lionel Messi, and if you ask your LLM about Lionel Messi, there is no AGI here. Right? So it won't be able to answer questions about Lionel Messi. As simple as that. Okay, so in other words, the information in your training set has somehow been stored in the weights of your LLM. But otherwise, there's like, no way for us to be able to retrieve that information by prompting. So one immediate question is that, okay, so there such information is being stored, how it is being stored, what is really going on? The short answer is, in many cases, we don't know. Right? And we'll cover some of those ideas in the future lectures. How we can localize information, what is really going on inside our model. But even if we assume that information is stored somehow, maybe on a set of parameters, a combination of parameters, but somehow in the model, this causes an immediate problem, right? And that immediate problem is that information changes. And so if you are training on Wikipedia, like Wikipedia information changes. Maybe if you ask your LLM, has Messi won a World Cup 2 years ago, it should say no, but a year ago it should say yes. And so information changes. So therefore, we need to constantly update model weights. You may say, okay, some information is static, fine, but again, there's a lot of things going on, right? So there's a lot of new information, new knowledge. Maybe some old knowledge is not valid anymore. Then that coupled with the fact that we don't really know where the information is stored and how the information is stored in the model, immediately brings us this really fundamental problem that we need to perhaps repeatedly fine-tune our model in order to have some decent model with most up-to-date information. We need repeated fine-tuning. And this is not good for many reasons, but because, first of all, since we really don't know how the information is being stored in the model weights, when you're fine-tuning, let's say if you're using LORA, are you really targeting the parts of the model that is responsible for that information? If you're not using LORA, it's like in terms of the compute, it is huge. If you do fine-tuning, maybe you'll overfit. Maybe you'll mess up your model performance on other instances. It is very delicate, right? So you need to constantly worry about what is really going on. So RAGs, it's a way to deal with this problem by adding some quote-unquote non-parametric memory to a pre-trained LLM. Adding non-parametric, and I'll explain where this terminology comes from, memory to a pre-trained LLM. So let's look at different parts of RAG. Retrieval, augmented, generation. So there are basically 3 steps: retrieve, augment, generate. So in RAG, we assume we have an ocean of documents, an ocean of maybe relevant articles, relevant text to whatever we have. And these documents, they can change. You have like a new page on Wikipedia, that's fine. It is not engraved in model parameter. That's a separate entity, your ocean of documents. So when a query comes, the first part is retrieve. What are the most relevant documents to that particular query? So that's basically the first step. Step 1, retrieve most relevant, or K in many cases, most relevant documents to a query. And we have studied this problem quite a lot before LLMs. This is just search. Right? So there are different ways of, let's say, if you go to any search engine, that's basically retrieval of the information. Right? So it doesn't really process the information. It's provides the most relevant sources of data for you. for you to process. There are different ways of doing fast retrieval, because you want this step to be really fast, right? So you don't, because potentially it's like oceans of documents that you have, like a lot of samples here. So there are different ideas. Many of them, they are based on embeddings, meaning that you have an embedding for your query. You represent it with a vector. You can use BERT, like we have covered BERT in this class. You look at the CLS token of BERT, you get a vector for that query. And then you already have computed embeddings for different parts of your documents, depending on how you like, chop it up. You get like these different embeddings, and then you do embedding matching. Based on the similarities of different embeddings, you can pick the top K nearest neighbors. But you can also do keyword matching. You don't have to like look at embeddings. Let's say if you're talking about Lionel Messi, maybe you can, first prune out, articles about Lionel Messi, and then, maybe combine with the embeddings. You can do a lot of different, processes in terms of retrieving most relevant documents. Okay. So that's basically the non-parametric part. Right? The K nearest neighbor that you have, the K nearest document that you find. Okay, and then we go to the next step, augment. Just augment these documents to your query. So now you have a query, then you have K relevant documents. These are K, perhaps like most similar or most relevant documents, K most similar or relevant documents. And then you have this as the input to your LLM. But your LLM doesn't have to keep up to date in terms of the knowledge. So your LLM in this view is like a processing engine that can maybe has some basic knowledge integrated in it, engraved in it, but it can take into account some up-to-date information with your query, plus some basic information in its weights, and provide some reasonable solutions, reasonable responses. That's basically the idea of RAG. Okay. So how do we characterize such a model? It is actually quite simple. So let's say, let's look at the RAG for a model that generates sequences. And then I'll talk about the RAG that is used for generating tokens. Very similar ideas. Okay. So if you look at the probability distribution of a sequence, let's say you want to see what is the likelihood of generating a particular sequence. I know we are running late, but hold on 2 minutes. What is the chance of generating a sequence Y given an input X? Before, your LLM was just doing it. But now I have some additional information. Let's say my P theta is my LLM. Theta is the set of parameters that I have in my LLM. I'm going to look at the probability of Y generated by X if I add the document ZI, a relevant document, as the input, and multiply it with the similarity of that document with my X. And I'll sum it up over all documents in my top K similarity. So this can be just as simple as like how relevant a document is to that query, multiplied by, if I had that as my input, as the context in my model, with that query, what would be the probability of that output? And I combine it. and I train my model based on that. For token generation, the idea again is quite similar. So you're generating the next token using your model. I is the next token, token I, given X, given a particular relevant document, and given all of the previous tokens that have been generated, you multiply by the similarity, by the relevance of that document to your query, and then you sum it up. And you do that for all tokens. And this Z again is the top K most relevant documents. That's it. You train your model based on this, then you don't really, in many cases, need to keep your model up to date. You can keep your documents up to date. Obviously, you know, there's a trade-off. And even RAG-based models, they are not perfect because the output is a combination of some information already engraved in the pre-trained model, plus some information in the documents that you're putting as the input to the model context. Since we really don't understand how such information is being encoded, then it is hard to predict when RAG is providing the correct answer or incorrect answer. And that's one of the ongoing research questions that people are working. Okay, so what is in-context learning? It's very easy. So it has been observed empirically that the model learns to do a particular downstream task by conditioning on a prompt with input-output examples. If you are giving more examples of a particular downstream task, the model has an easier job to do that. That's called in-context learning. The model learns to do a downstream task by conditioning on a prompt with input-output examples. Okay, for example, if you want your model to generate some particular responses to particular questions, you can add some templates, some demonstrations in your prompt. You can say, here's my question that I want you to answer, and here are some example question and answers that I give you. And in many cases, that helps the model generate better responses. It is basically prompt engineering. So you are providing some information in the prompt. Part of prompt engineering. And how it works, why it works, it is unclear in many instances. Some explanations of why such demonstration data in the prompt can be helpful has been given by this particular paper that we posted on the Coursera page. And basically, roughly speaking, what they are arguing, which is sensible, is that during pre-training, the language model learns some latent concepts of the underlying data set. So if you're pre-training a huge large language model on a huge data set, obviously the model learns about the structure of the language. But if you have a particular data set in a particular format and you're finding your language model on that data set, potentially it learns some shared concepts from that data set during the fine-tuning. And authors argue a similar phenomena is likely happening when you are putting some examples in your prompt, that the model somehow learns, even by just few examples, some shared concepts, and that helps model in terms of generating better responses to the questions given in the prompt. Really hand-wavy, but that's the one explanation that is being given. And in the paper, they have like some simpler analytical formulation of this, not obviously for practical language models, but on simpler setups, but they show in fact this can happen. Let me just briefly write this intuition. Again, as I'm highlighting here, it is pretty hand-wavy that during pre-training, language model learns some latent concepts of the underlying data sets. As an example, if you have a language model trained on Wikibios, in the Wikibios, in many samples after the name, you get immediately the nationality of the person X, from this particular country, and you learn such shared, and after that maybe occupation. What is the occupation of this individual? These are the shared concepts that are learned, meaning that if you want your model to complete a sentence and you start with the name, more likely it will produce a token related to the nationality, and after that related to the occupation of that individual. These are like the shared concepts inferred because of the structure that you have in your fine-tuning. And they argue that in context examples, language model infers some shared concepts from those examples. And this is one way to think about why such examples can be helpful. And they have like some theory, but in very simplistic setup that I won't cover. Okay, it makes sensible, right? You provide some examples about a type of the task that you want your language model to succeed, and it helps the language model. It's kind of sensible, good, intuitive. But then this paper comes, there's another paper by Min et al. That they have a very interesting, again, prompt engineering paper, right? So that's, they play with the prompt, how the model behaves. They show even if you provide incorrect examples, but with the right format, the performance is more or less the same as if you provided correct examples. So therefore, it's more important to have maybe the similar formats in terms of your questions and similar formats in terms of your answers, in terms of their marginal distributions. But maybe their coupling is not very important. You can like have the format that you want for your questions and answers, but maybe the incorrect coupling between them. And still you get some improvement in the performance compared to the basic language model, which can be surprising, right? Because, and I would say somehow can potentially, partially contradict the previous result, that these shared concepts are not about like the joint distribution of your question and answers that you provide in the prompt. Perhaps like no, it is more granular in terms of maybe some concepts with respect to the formatting of your questions and some concepts with respect to the formatting of your responses, but nothing in terms of coupling the two. All right, so let me just summarize what I mentioned. Basically, they say if the format of questions and answers are good, but the pairing question answer is incorrect, still see improvement in performance by providing such incorrect question answering examples, but with a proper marginal distributions for questions and answers. Again, this kind of shows we literally don't know much about the underlying mechanics of these language models. There's a lot that we don't know than we do know. And prompt engineering is one way just to see the extent of issues that we can have in these models because of the lack of knowledge that we have with respect to how they store information, how they process information, how they generate information. So that's basically all I have in terms of in-context learning. I'll pause here, see if there are any questions. Otherwise, I'll cover one more topic of chain of thoughts. Again, that's another technique of prompt engineering that is very commonly used in language models before moving to the next topic. Any questions? Yes.
So this I haven't read the paper very well, but it seems like it highly depends on what kind of task you're performing in context learning tool. Like if it was some task with very deterministic answer, like let's say addition, and if I give it incorrect addition, like if I say A plus B and C, then it for sure won't learn anything in context, right? Because incorrect answer to addition means that.
Yeah, absolutely. Right. So the question, if I understand, is that what is the role of particular task in the analysis? Yeah. And I totally agree. I don't think these results are in many cases generalizable. It really depends on the nature of the task. Is it like deterministic, for example, arithmetics that you want to do? Or is there some maybe probabilistic reasoning that you want to have with respect to some questions? Again, that's the limitation of, in my opinion, the analysis based on prompt engineering, because you're as good as like the set of prompts and set of tasks that you consider. Excellent. So let me move on to the next topic. You see how quick it was, in context learning, like 2 minutes, 3 minutes. Chain of thoughts, it will take maybe 3 minutes, maybe more. All right. Okay, so the next one is chain of thought prompting, or for short, it is called COT. So in standard prompting, so we usually have, let's say, a question as an input to the model. And then, as I mentioned, we have like some demonstration examples saying that, okay, here is another question. So these are examples. let's say you're asking some basic math question, and you give your model some demonstration examples. Let me just, to really give you a feeling what I'm talking about, just write one such example. Okay, I'll use my own name. Soheil has 5 tennis balls. He buys 2 more cans of tennis balls. Each can has 3 balls. How many tennis balls does he have? Okay, so what's the answer? This will be in the final video. 11, right? So there's like 5, 3 cans, two cans of 3, 2 times 3, 6, 6 plus 5, 11. Here's the demonstration example. So this whole thing goes into your prompt. Like, this is your prompt. And this goes to LLM. And you want to get an answer to the question that you are asking with these demonstrative examples. You know, that's partially what I meant by in context learning, right? So you're giving like some examples to your LLM, and you get an answer and see if it works or not. Okay, so what people have observed in chain of thought is that instead of giving just a final answer in my demonstration example, if I tell the model how such a response is being calculated, that helps the output. That's it. That is called chain of thoughts. Okay. So in chain of thought prompting, again, I'm going to have my question that I have for the LLM. Okay, now for my demonstration, I'm going to use the same question. So it has etc., etc. And for my answer, instead of saying 11, I would say, okay, Soheil started with 5 balls, 2 cans of 3 balls, basically give 6 balls. Therefore, I'm just like, shortening it. You write in language, right? Therefore, overall, you get 5 plus 6, 11. Okay. So here's your answer in your demonstration example. And this whole thing goes to the LLM. And you get your response for this particular question that you have. And it improves quite a bit. Really simple, right? Instead of just giving the final answer in your in-context example, just give some more explanation. So I love the LLM community because they come up with like amazing names, like chain of thoughts. Right? So if you literally had no idea about it, you would, probably have had some other concepts and probably more complex ways of dealing with LLM. But that's basically it, right? Just explain your answer in the demonstration example. Even simpler, you can just add let's think step by step. Before each answer, just tell your model to think step by step. Before each answer. This is sometimes called zero-shot chain of thought because you don't actually give any demonstration example anymore. You're just asking your model to think step by step. I know some of you are smiling, but the paper is actually showing some significant improvements over the baseline, and I'm sure it has been cited like a lot of times. Again, it may not look like deep science. It is prompt engineering, but we should have them because they can give some empirical observations about the model. Right? So they may not be like technically deep or complex, but at least these are like some empirical observations that can help us to see what is really going on. Right? I hope with these examples you get a feeling that we literally don't know much about language models. We are just scaling them up, and that is all. Right? So how they work, why they don't work, it is an active area of research, which is great for all of you because it means you will have jobs in the next decade or so. So here we have no examples, demonstration examples in prompt. To be more specific, the way that the prompt works, you have a question and you say, okay, in the answer, you start, let's think step by step. This is your prompt. It goes to LLM, it generates something. And then you ask your LLM one more time, saying that, okay, here was your thinking step by step. And you add, therefore, the final answer is. And then you put it to the LLM to get the final answer.